our topic today will be some practicalities of FEA boundary conditions. In a nutshell, like going beyond what is taught in the classroom and in the first courses, but start to think like an engineer and applying our engineering senses into building our FEA models. So let's get started. A little bit about me. I'm Guillermo Giraldo Fernandez. I'm a Colombian engineer. I studied mechatronics at the university, but being there, I started learning FEA since the theory and first practical applications, and I have been working on it since then. So it's been around 15 years of experience with FEA, both in the academy, but also in practical consultancy and industry projects. Right now, I am a consultant with my own company here in the country, Zenit SAS, where we provide design and analysis services for domestic but also foreign companies. And also, I am a customer support agent for SimScale, which is a simulation in the cloud provider platform. And in there, I am one of the FEA specialists, so dealing with all these customer support and problematic cases, application, engineering, and developing, product development support, and all of things FEA. So I'm very happy that I can contribute with my experience and my point of view in this company, which is really awesome. About my profile, I have practical knowledge and experience in a few FEA areas. So nonlinear FEA simulations, plasticity, creep, large deformations and rotations, physical contacts, and all of that stuff combined. Thermomechanical analysis also with nonlinear FEA, and also fracture mechanics, linear and nonlinear fracture mechanics analysis. That's basically what I do, what I specialize in consulting, on top of other stuff, non-FEA, such as design for industry, piping, analysis, and that type of things. So the goal of this talk is just to interchange some knowledge and experiences on my, say, 15 years of experience with FEA. In what I consider to be one of the most important aspects of building FEA models, which are the boundary conditions. We will discuss my point of view, which is based on my professional experience, especially on how to practically think about boundary conditions, or from saying in other terms, how to apply our engineering sense into building our models in the part of the boundary conditions, especially looking at or thinking about the effect that the boundary conditions might have on the results of our FEA simulations. So, as a disclaimer, I don't consider myself like to know everything. So please, if you have any feedbacks or inputs, we have a chat here on the Zoom call. So if you have any questions or comments, just please feel free to write them out. If we can make a more interactive session, then you will be able to make the most out of it. So as an agenda, we will cover what are boundary conditions from my practical point of view approach. Then a first example. We will talk about loads and constraints and how they relate with each other, and what we can do when we are thinking about loads and constraints in our systems. We'll talk a little bit about symmetry conditions from a point of view that is very particular. And then we will see a couple more examples of the effects that the boundary conditions can have on practical applications. So let's get started. So what are boundary conditions? So when we start learning the theory behind FEA, or in general mathematical or physical modeling of, say, physical systems, In this case, let's say it's about the structural systems or solid mechanics. Then the physical behavior of the system is modeled through a differential equations. We can convert it into an integral equation, the weak form, the strong form to the weak form, and everything that we know from classroom, right? Then this differential equation is general. We need to apply it to a specific domain, which will be our system of interest. And this domain is limited by a boundary. So the boundary is the surface that surrounds our domain where we are applying our differential equations, right? That's where the term boundary conditions comes from. It's just what happens in this interface or in this surrounding surface. The differential equations on the domain are singular by themselves. Just a differential equation on this domain, it's not enough to find a solution, say a deformation solution or a stress field. So we need additional equations always to close the model. That's one way of saying it, and point to a particular solution. This means that the differential equation that describes the physics is not enough. We need to add these conditions on the boundary, which are additional equations with forces or pressures or constrained degrees of freedom, constrained displacements. And when we join all of these equations, then we arrive to a set of or a mathematical model that can be solved and leads to a particular solution, hopefully. So, but that's from the say the theoretical classroom point of view. What is we want to know what is actually a practical point of view. What are boundary conditions actually from the practical point of view? So from a practical or modeling point of view, we have a system that we need to analyze as engineers, right? We need to predict the behavior of this system. If it's a structural system, then we are interested in finding out what will be the deformations, what will be the stress levels, if the stress levels are on the safe according to some criteria, right? That's what we want to do. But actually, it is not practical to model a fully isolated system. So what would be a fully isolated system anyway? So say you have a building structure. So a building structure is supported on some foundations, which is also at the same time supported on the soil, right? But then the soil is really big. And then if you say grow this point of view, then the soil is part of a larger system of soil and what is surrounding. If there are rocks in the bedding and the ground and the subground layers, finally you go to the whole earth, which is what exerts the actual gravitational forces on our structure, right, to create our gravitational loads. But if we want to model, say, an isolated system of our structure, where do we draw this limit, right? That's the thing. It's never practical to draw a limit big enough that we don't have to use boundary conditions, say that the system, all the actions of the system, so all the loads in our structure are created naturally, included in the model. That's not practical. Instead, what we do as engineers is we focus on a subsystem or a component of an assembly, so we can do a more practical analysis. So the boundary conditions are those tools that we use to connect this isolated region that we will analyze from its surroundings. That's basically, so boundary conditions just capture the interactions in this interface between our domain of interest and its surroundings, so we don't have to model a fully isolated system that, if you start thinking about it, might include the whole universe. That's really not practical. So that's from a point of view what boundary conditions are, right? And that's the first takeaway that I want to give from this talk. So when you start thinking, okay, I need to analyze this component or this subsystem, because it might be an assembly of components, but think what are its surroundings. In other words, there are other engineering terms. For example, when you heard the term, what is the load environment? All that it means is how is the time variation of the effects that the outside of our limit, the effects or the loads that are imposed or acting on our system. Boundary conditions, the supports or the loads, and everything. All of these actions from something that we leave out from our model, but that interacts with our model. So anytime we identify such interaction, we need to create a boundary condition. So as a first example, let's say that we are contacted by this bike manufacturer, right? And they have this new design that they want to test before building the first prototypes. And they say, hey, you are an FEA analyst. I need some FEA simulations to help us improve our design before we start building our first test models or our first prototypes. So let's think about it in this, say, systematic way onto what we need to analyze, what is the environment, and what are the interactions between our system or our target component and its environment. So this is a picture of the bike under operation, right? It's a mountain bike. We have the rider. So what is the surrounding? What are the surroundings of our bike? And of course, our target component is the frame of the bike. So we can see that the bike assembly is running on the ground, right? That's our first interaction. So the ground is what provides the support and the reaction force against the weight that is supported by the bike, the weight of the bike transmitted through the wheels, and the weight of the rider transmitted to the bike frame, to the wheels, to the ground. So that's our surrounding. So we have two main interactions, let's say, the support that is provided by the ground, but also we have the interactions with the rider in terms of the loads that is imposed by the weight of the rider. So what are these points of interest, or where will we draw our line of our systems? So if we look at only the frame, we can see all the connecting points. So the first thing that we can see is the support points. So the first support point is here on the rear wheel, where there is a shaft support. So the back end of the frame is supported here. So that will be our first boundary condition, right? Because we will model the wheel, the hoop, the shaft. That one we modeled, only the frame. So that here we will have to apply our first boundary condition, right? Then the other support point is at the front, which is on the fork. So we won't model the fork or the handles or the front wheel, but then we see that the support is provided at this point, or at this joint between the fork and the front of the frame. So that's our interactions with respect to the floor. But then what are our loads? So when we remove the rider, what are the effects of the rider on the frame? So we have a weight that is applied on the pedals, that is transmitted through the pedals through a shaft into this cavity here where the shaft fits. We have a weight on the seat, and we also have a weight on the handles. So by identifying these 5 points of connection between our system and its surroundings, we can create an isolated model that only contains the frame. So we will first apply a vertical force where the seat connects. We will apply another vertical force where the handle connects, and we will apply a vertical force where the pedal shaft connects. We will also use a hinge constraint on the rear shaft. A hinge constraint is no more than a constraint that will allow it to rotate around the axis of the shaft, because otherwise it will be over constrained. We will talk about this aspect in a little bit. And then in the front where the fork is, we will use a symmetry plane boundary conditions. What this means is that we will only restrict the displacement in the normal direction to the direction that is normal. So if this is the plane of the end face, then it can only move in the normal direction. We cannot use a vertical constraint here or a constraint aligned with the principal planes just because it is rotated. So in this case, we use a symmetry plane. I've actually built this model in SimScale FEA solver, and you can see here the results of such simulation. So I have the load that is applied here, I have the load that is applied here, and I have the load that is applied here, and I have a hinge constraint here, and I have a symmetry constraint here. And you can see that by doing this, I can capture most of the interactions, the bending of the parts, and the movement. The system is not over constrained. You can see that these parts are not completely fixed, but they can move in the actual direction, and there's also some rotations involved. I consider this to be a very realistic model of the bike frame, and what allows us to do our assessment, like find our points of higher stress and analyze here what is happening, and maybe propose some changes to improve this design. So this is our first example. So when we are trying to build our FEA models, always try to find the points where we will do the cut from the whole system, from the whole surroundings into our system, and analyze what is the behavior at each point and what is the interaction between our system and the surroundings. Next topic that I wanted to touch about boundary conditions is the relations between loads and constraints. So we've been told, or we've been taught that there are two types of boundary conditions. Some codes call some of them loads and the other boundary conditions, or loads and constraints, or boundary conditions altogether. But some they have some mathematical representations. So some are forces, and some forces or loads that can be converted into forces, like body forces or pressures, thermal loading, etc. And the other are constraints, which are only the degrees of freedom or the displacement that we prescribe. So it can be displacements that are constrained to zero, or that have some predefined value, some non-zero predefined value. So these are loads and constraints. So how they relate, and what I think is a very good engineering approach into thinking about loads and constraints. So to start the discussion, let's remember what it's Saint-Venant's principle, which is impossible not to talk about this topic when talking about boundary conditions. So basically what Saint-Venant's principle says is that if we have a system, think of our bike or however system it is, and if we replace one of the loads for an equivalent load, or you replace one boundary condition for an equivalent boundary condition, then the stresses on regions that are far away or at a sufficient distance from these boundary conditions are not altered or do not change. So the interpretation of this principle is that we can have virtually the same behavior of a component in terms of its overall deformations and the stresses in the regions away from the boundary conditions, even if we change the boundary conditions. So in other words, there is not only one way of modeling a system. So if you think about our bike example, there are many different boundary conditions that we can apply at each one of these interface points or these boundary points that will produce the same behavior or an equivalent behavior of response on my structure or on my system. And that's very important. That's very important because that opens possibilities for us as engineers to try different things depending on the scenario and the situation, and seeing what is the not only the most realistic, because the results would be the same, but of finding the most convenient way of modeling with the aim of achieving the results that you want or that you need. We will see more about that in a moment. So, but what are two equivalent boundary conditions? So on forces, you can replace pressures with equivalent forces. That's something we know how to do, or tractions, replace them with forces, or moments. We can replace them with pairs of forces. We know that, but I want to talk about a very particular application of this, and what are two equivalent boundary conditions, but talking one of them being a force and one of them being a constraint or an imposed displacement. And we will see that that is completely possible. And for that, I have this example, which is a simple, say, beam under a cantilever beam under bending action, but I have modeled it in two ways. So in the model on the left, I have okay, both of them have the back region. Here the back region is fixed support, so all of the degrees of freedom are fixed to 0. But in this end, on the left model, I have applied a load, a force on the two nodes. But on the right one, what I did is not to apply a force, but to apply a displacement on these two nodes where I applied the forces. So actually what I did, and I will see in a moment, is that I first run the one with the force. I measured the displacement on these points, and in this case, I removed the forces. And what I did was to apply the displacement that I measured on the first model. And you can see from the stress distribution and the stress scale, this is the normal stress, the normal bending stress, sigma xx. And you can see that the ranges or the levels of the stresses are the same. So I was able to replace a force boundary condition and get an exactly the same behavior without using the force. So this might seem obvious if you think about it, but that has some very important implications that we will mention in a moment. So you can see here that what I did is I applied a 1K load per node, and then I measured the displacement in the plane, so dx and dc on the 2 points. You can see here the results from the displacement results on the nodes 5 and 7 on the simulation. And what I did is just run this second simulation, but in this case I applied this as the inputs, this same displacement, and measure the reaction forces on the on the 2 points. You can see here that the nodal reactions is what is delivered in this table in the same 5 and 7 nodes, and you can see that my reaction force is the same in the C direction than the 1K that I applied.
Guillermo, what do you mean by imposed displacement?
Yes, thank you. I just saw the pop-up in the chat. So rhyme. So imposed displacement means that you, as a boundary condition, take these nodes and say in your program that the dx and this and dc of these nodes will have these values. It's similar. Yes, it is core raster. It is core raster output. I simulated this particular case with core raster. Yeah, that's right. Good catch. So instead of saying that in this node you have a force, say in this is node 5 and node 7, right? In the first one I apply 1K and 1K, 1 kilonewton and 1 kilonewton load as boundary condition. So in the second case, what you say to the FEA solver is that it won't apply a load, but it will enforce that these nodes will move with this vector that is here. That's an option of the FEA solvers. So as inputs, you don't have to only apply forces, but you can also create the deformations by applying what is called imposed displacements. So Jeremy says, having to set forces at this node is an example of the input file depending on the mesh, which was discussed in the very previous talk about things. Yes, that's right. That's very interesting, Jeremy. Thank you. So did that answer your question, Ryan? You can reply in the chat, please. Okay, let's continue. Do you mean that we tell the solver about the needed displacement? Yes, but the needed displacement not on the whole part, but only on these 2 points, node 5 and 7. You can tell the solver to deform it in that amount. Yes, that's right. It's very similar to what we do on the fixed support boundary conditions. So what we do in the fixed support boundary conditions is to tell them that the displacement is 0. So the displacement in X, Y, and Z components, which are the degrees of freedom, they are all equal to 0. In this case, they are also imposed, but the value given is not 0, but it's a non-zero value. Yeah, that's
but I didn't understand what is the importance to eliminate the displacement, to eliminate the force, and telling the solver about the displacement. Why we are doing this?
Yes, we'll get there in a moment. But there are many advantages of it. So the first one is to be able to think and open your mind that there is not only one way of modeling a system, and that there are equivalent boundary conditions. So that's the first point that I want to prove here.
So maybe do you mean that what I want to say that maybe you want to measure the maximal displacement or the maximal force? So I mean, you will precise the displacement and then you will apply the force, or I didn't understand this point, to be honest.
Yes, we will give some practical applications of this. So for the moment, it's important you have Jeremy says that if you think about it, it's about the uniqueness of the solution. So if you get a displacement with a certain force, then that same displacement has to give the same force. Yes, that's right. That's right. So it's a unique solution, but with two different, we can arrive to the same solution with two different boundary conditions. So the idea is that, or the point that I want to prove here is that do not think on the boundary condition as being the only one possible way to do it, but always explore what are the possible modeling approaches for your system. And one very important to me application of this principle is in nonlinear finite element simulations. Sometimes applying a force when you have, for example, two parts that are interacting through a physical contact. If the parts are not initially under contact and you apply a force, then as the displacement is constrained, it's not constrained because the physical contact is not active. Then what you get is a force on a rigid body motion, right? So the displacement is infinite because the physical contact is not active. So apparently you will get a divergence on your solver, and apparently there is no solution to this. So if you apply this principle and you think, okay, I'm applying a force because I've been told that my assembly that I am analyzing has to withstand for a load of some value, right? That's what you want to. What you need to model. You need to find the response against this load, but then you cannot get the response because you are getting a divergence, right? So if you think about it in this way, say, okay, how can this is what is happening. I'm applying a force and there is no reaction to consider that force, and I'm getting an infinite displacement. So let's switch the boundary conditions that I am applying, and maybe I can replace this force with an imposed displacement, which will control the deformations, right? Because I'm imposing the displacement. I won't get the divergence. And then what I will do to know the force is to measure the force. So let's move. Let's explain here. So what I have proven here is that sometimes the loads and constraints are interchangeable. And sometimes what I mentioned is that a very important application is displacement-driven simulations, which help a lot to converge to nonlinear solvers. So the apply force of the approach, the workflow of applying a force and measuring the displacements is switched to the opposite, which is, okay, now we will apply a displacement and measure the force. And in the meantime, we help the nonlinear solver to converge. And as we saw, it's the same unique solution that we are looking. We just give it the way around and found the solution to overcome the difficulty that sometimes we introduce through our model. Does it give some context? Is it clear, the intention? So I want you to think about it this way, that I just say that sometimes you just keep in mind that for a system where you apply a load and this load produces the displacement, maybe there is a way. I'm not sure it's not in every case, but you can replace this load and that can give you some benefits. So that's very important to bear in mind and to know about load and constraints. So try not to be close in that there's loads, there is constraints, there's my fixed support, and that's how it should be. But there are more ways to get to that get to that unique solution. And depending on the circumstances, one can be more beneficial than the other ones. So it's important to just keep that in mind, that there are more options, and always keep researching and keep thinking about your models in this way. And that's a very important part of the boundary conditions. Okay. let's move ahead. Another example of this is the submodeling technique. So the submodeling is basically we take our system and we cut it, say with a cube or with a sphere. And what is, how are the loads transmitted to our submodel? Just through displacements. So just by transmitting the displacement of this cutting surface, then the internal response or the internal behavior will be the same. And that's a very important application in cases where we can just switch loads for constraints. Because if we were to transmit, say, the stresses or the loads on the surface, we wouldn't have any suppression of the rigid body motions, right? And then we will also not be able to solve this system of equations, right? So in the case of modeling, they also apply a principle that is very close to what we have been talking until right now, just to overcome the difficulties on the numerics to solve, say, a system with not enough constraint, or a system that has rigid body motions that is not properly constrained. Again, remember the other case of the displacement driven nonlinear simulation, when we are also fighting the solver, which it cannot easily converge sometimes under their force loadings. Okay, next topic that I wanted to touch on is symmetry conditions. And symmetry conditions are more useful than one usually thinks. So traditionally, when we talk about symmetry conditions, we always, we've been all told, or we've been all teach that symmetries are used in the model to reduce the model size. You just leverage symmetry to reduce the size of the mesh. You just cut your mesh in half, or in a quarter, or an eighth. Then you will consume less memory. The simulation will be cheaper and will be faster, and etc. And that's a nice thing to have in your model, that it runs faster. But I want you to think that symmetry conditions sometimes can be more useful than that, and that sometimes we can leverage symmetry conditions to enforce a more realistic behavior in a model. And what I mean by that is that we are used, or they say that our direct way of approaching modeling is, okay, I need to constrain the rigid body motion, so I will just throw some fixed support here and here and here, and in those places, so I get away that now I won't get any rigid body motion, and my model is properly constrained. But there is also a problem of over-constraining the model. So constraining the model in directions or in deformations that do not happen in real life, and that we are inducing a response or a stress distribution or some deformation modes that are not realistic, that do not happen in real life, just because our boundary conditions or these interactions with the surroundings are not just fixed, infinitely rigid supports. So that's something very important to keep in mind. And one thing that can help us sometimes, or in some cases, in making our model more realistic, is the use of symmetry conditions, and we will see a very clear example of this right now. So let's think about a cylindrical pressure vessel. Say this is a pipe, right? Subject to an internal pressure caused by a pressurized fluid, say water or oil or gas or air or whatever you have. When we analyze this, we go to a code, say piping code or pressure vessel code, and they give us the principal stresses in the pipe wall, and these principal stresses that are developed in this cylindrical are, say, some tangential stress or hoop stress, or reed stress, which is sigma sub theta. We place ourselves in this cylindrical coordinate system with C the longitudinal, R the radial, and theta the tangential direction. So this hoop stress is given by this equation, which is the one that tries to inflate the pipe and make it grow radially. So for this stress to develop in the pipe has to be able to grow radially, right? So if you get to this end, say, okay, I need to I'm gonna just throw a fixed support on this end. So I'm just gonna add a fixed support in this whole face, right? Because I need to constrain my rigid body motions. So what happens in this case is that, okay, I'm constraining the rigid body motions, but I am also constraining the pipe from growing radially, so it cannot anymore grow in this direction, right? Because this phase or this line is completely fixed, and this growth cannot happen. So what will happen, say if we leave this end free, is that the pipe here doesn't grow, but it tries to go radially, and we get something like that. And this bending will introduce an additional bending stress that is not considered in the code, or actually it's not realistic, unless there is an actual, say, bracing here, or some type of pipe support that is bracing the pipe and preventing it from growing radially. But if that doesn't exist, then our naive boundary condition here is introducing additional stresses that are not realistic, right? Same for this axial stress. This axial stress is created also by the internal pressure, but say that the end caps of the pressure vessel or the bendings, they create an stress, right? An axial stress, because as the fluid is contained, the pressure makes it try to grow actually, and then the resistance to this growth is what creates this axial stress, and they are computed analytically. And if we want to use an FEA model to compute such stresses and compare, say, to the code, then we need to be prepared for these things to happen. So we cannot naively just say, as I said, apply a fixed support here and apply a fixed support on the other end, and I will get away with that. That won't work. So one example application of this is, for example, fracture mechanics. Let's say this pipe has a fracture here, right? And when we perform fracture mechanics analysis, we need to subject the crack to only the principal stresses, right, that are trying to open this crack. So the stress that tries to open this crack is this tangential stress, right? Or if the crack is in this direction, then the stresses in this direction are what try to open the crack, right? And we need to, in our FEA model, only include these stresses. Otherwise, our solution will be valid, say, with the current tools that we have to analyze this, the FAD assessment, for example, the failure assessment diagram. So this is an example application on why it's important to think the effects that this boundary condition will have on my system. It's a little bit of an advanced example, but I think that it's very clear and that it illustrates very well that we need to really take care about these things, about our loads and our boundary conditions when planning our model. and what we need to achieve and what we need to include to get to the results. So what boundary conditions should we apply in order to develop only principal stresses in this model? It is kind of difficult to model a whole pipe, get it? Maybe a remote condition here, remote point condition that allows to grow, but that it's up to debate the effects that these connection points have. So I'm going to give you one solution based on symmetry that you can use in such case. So in this case, I also built this one with Coracer for the people that like Coracer. So what I did to achieve to have only these two principal stresses is, okay, I model a quarter of the pipe. Then this phase will have a symmetry in the x direction. In the x direction, Jeremy says, I can show you. Yeah, thank you so much. That will be really nice to see how we can solve it and only get the principal stresses. That will be nice to learn a new technique. So in this phase that we cut normal to x, we will apply only deformations like a symmetry, only in the normal direction of the cut plane. Same for the symmetry with respect to y, and the symmetry with respect to c, which is this phase. So each phase has only one constraint. The internal phase subject to the pressure, but then the end phase I will subject it also to the pressure to create the actual stress. We could, for example, create a cover here, say a cover here, and apply a pressure. Yeah, but that's equivalent. I will just take this phase and apply a pressure of the stress, the pressure that I know that is developed due to the axial. And let's see the results. So you can see here in my results how the pipe nicely just grows in the radial direction. You can see this end, how it grows aligned with the x direction, and this one grows in the y direction, and how it nicely only grows in the it just inflates, right? It cannot be seen. You can see here a little bit with the separation, but it also only grows in the axial direction a little bit. But due to the other effects, it doesn't really grow. It actually shrinks due to the Poisson effect, but that's another story. But you can see how nicely I get the deformation that I wanted to have by leveraging the symmetry conditions. And to check the stresses that I expected are developed, then you can see here I did a little computation. So the tangential stress, which is the principal third stress, the main stress, it's called this way in Coracer, should be 20 megapascals, and you can see that I am getting 20 megapascals on the inner face and 18 megapascal on the outer face, which is expected. And about the axial stress, you can see I get the second principal stress, and I get an almost constant stresses across the section of 10, which is what I expected. So you can see that if I don't have the example, but if I had just fixed the ends, I wouldn't have gotten such a nice results that are in compliance. So right now, if I need to include that crack, I can include it here, say, or include it here in this end, and my crack is ready for the fracture mechanics analysis, for example, or whatever you need to do with this pipe. Maybe include a defect or whatever you need. So we have 10 minutes left. Let's go quickly through our last example. So, and the last example that I wanted to show is in dynamics. So we have the example of a electric motor rotor that we want to analyze for critical rotational speeds. For this, we have such a Campbell diagram, which plots the evolution of the natural frequencies of oscillations because we are including the gyroscopic effects due to the rotational speed. So as we accelerate, you can see that some of the frequencies, they change. And if we plot, say, a line where 1 hertz corresponds with 1 rotation, then we can find this point where at this speed, if we operate at this speed, we can expect some resonance. So it's very important, as natural frequencies depend directly on the stiffness. It is very, very, very important how we model the boundary conditions in this case. So this is our rotor. You can see it's a squirrel cage rotor. So we have these two faces where the bearings are located, where the shaft is veered, and also the output coupling where the end shaft is connected. So all the power is transmitted through this face, through the cube here. Here we have bearings, and bearings we know that they allow the rotation, and they only fix in the displacements. So it depends on each tool, each FEA tool, how you will get to this behavior, maybe with a hinge constraint, maybe with a remote point condition, connection. There are many ways to do it, to achieve it, but it's very important that we model it as realistic as possible. So say, for example, that, okay, all that I will do is to fix this end phase, say I fix this all end phase. Of course, that will get rid of the rigid body motions, but will it be realistic? I mean, if you think about the torsional rigidity of the shaft, it's not the same if you fix it here and here with this length that, say, you, for example, fix it here. Because if you reduce the length, then the stiffness will not be the same, and you will be affecting the stiffness and the natural frequency. Same for the bending modes. So if you fix at the ends, the length is longer, right? And then you have a longer shaft, or say a longer beam, than if you fix in the correct positions. And then it will be more flexible, because you will have lower natural frequencies, and you are inducing errors on your model. So that's a very important thing. Just try to be as realistic as possible. And when you try to do simplifications, think very thoroughly on what errors you are inducing onto the model. And you can see here that by applying these boundary conditions that I just described, we are able to capture all of these nice modes. So torsional modes, you can see with the fix at the end where the power is actually transmitted. Some flexural modes, you can see that the correct lengths are captured in these directions, and all of these flexural, second order flexural modes. So very, very important lesson there. And that completes the example. And this is the last slide, so your last chance to make questions or comments. We have 6 minutes left.
Excellent. Thank you so much, Guillermo.
Welcome.
Any more questions before we wrap it up? I know it was a hard day, 4 sessions today, which is a record. So
just congratulations, Guillermo, because those cases that you pointed out are very important. There's subtle differences that can lead to very different results.
Thank you so much, Jeremy. Thank you. I'm glad I'm glad that the examples were properly selected. Thank you so much.